Hello, students. We've made it to the fourth and last lesson in Module 10, Multiple Linear Regression. If you recall, when we discussed simple linear regression, it was a big lesson. In fact, we had 2 lecture videos, a lot of details there for the linear model fit, similarly for the hypothesis testing. Well, one could go through multiple linear regression in a similar fashion. For us, we want to think about multiple linear regression as an extension of simple linear regression. Therefore, I consider this video to be really an overview. So the objectives of this lesson are to fit a multiple linear regression model, also check the model assumptions with diagnostic tools. You might recall with simple linear regression, we had X, which was our independent or explanatory variable. We had Y, which is our dependent or response variable. This is 2 different, really, sets of terminology for the same thing. With multiple linear regression, here we have P explanatory variables, x1 through xp. P is at least 2. We still have 1 response variable. And we assume here that yi is beta 0 plus beta 1 x1i plus beta 2 x2i out to beta p plus xpi. And then we have this plus epsilon I. So here I goes from 1 to n, the number of observations we have, and then epsilon 1 through epsilon n. This is our random noise. Comes from the normal distribution, mean 0, standard deviation, sigma. Similar to simple linear regression, the expected value of y or predicted value of y given some observed x1 through xp is here we take beta 0 plus beta 1 x1 plus beta 2 x2 out to beta p xp. Now, the interpretation of the coefficients, well, beta 0, just like with simple linear regression, this is our intercept, but the others, beta 1, beta 2, beta 3 out to beta p, beta j, this is the estimated change in y corresponding to a 1-unit change in xj when all other variables are held constant. Now, it's an important remark that ideally the explanatory variables are all correlated with capital Y, but not with each other. Okay, the good news is in R, the multiple linear regression fit is done using this LM function, just like the simple linear regression fit. Now, I created an example. It's not using real data. I really just want to show you the summary table, talk about it a little bit, and then we can look at some of the other outputs that really correspond to something we've already discussed in the simple linear regression case. Okay, so here I have 3 is p. That's the number of the xi's. I have x1, x2, x3. And you can see how I've called this here. I've used this linear model function, and then I asked for a summary. Well, really the first thing to look at is here, the p-value on the F statistic. So this small p-value says the regression model is statistically significant. This would be as compared to the linear model where all of the beta 1, beta 2, beta 3 are 0, and all we have is the intercept. So here we have a statistically significant model. Then we could look at this R squared. So here, R squared is 0.7389. This gives us the proportion of the variation that's explained by the linear model. Okay, what else do we see? Well, here we have these p-values corresponding to the individual t-tests for the different coefficients. So you notice, at least at the alpha's 0.05 significance level, this one, this one, this one are statistically significant, whereas this one is not statistically significant. So based on these p-values, we can conclude that beta 0, the intercept, beta 1, and beta 3 are not equal to 0. We cannot conclude that about beta 2. We have a high p-value. We see the estimates here. The estimate, beta 2 hat, is minus 0.2043. However, based on this p-value, we cannot say that beta 2 is non-zero. Maybe I will add above, these are beta I hats. Next, well, we can see the 95% confidence intervals. These are the 95% confidence intervals for the coefficients. We have the confidence interval for beta 0. And then I will copy and paste this 3 times. Okay, so we have a confidence interval for beta 0, the next one, confidence interval for beta 1, the next one for beta 2, and the last one for beta 3. Just as a note, if you look in the confidence interval for beta 2, you notice that 0 is in this confidence interval. This is the one where we failed to reject the null, so we can't say that beta 2 is non-zero. The last thing I want to mention is our diagnostic tests. These we talked about in the very last lesson. We talked about them for simple linear regression. We had the same diagnostic tests in multiple linear regression. So we have the Shapiro-Wilk test on the residuals. Recall that for this test, H0, is that the residuals follow a normal distribution, whereas the alternative, I just copied and pasted, and then I can add the words, do not follow a normal distribution. So in this diagnostic test, we want a high p-value. We want to fail to reject the null. And this is what we see here. We fail to reject H0. This is a good thing for the Shapiro-Wilk test. Maybe I'll write that. We fail to reject H0. Which makes us happy in multiple linear regression. Now, the final 2 things we had were these plots. Here was our QQ plot, which was for the residuals comparing to a normal distribution. This looks pretty good. And then we had this plot where we plot the fitted values across the x-axis, the residuals across the y-axis. We're looking for mean 0. We're looking for no clear pattern in the plot. And then we're looking for the variance to be more or less the same. So this looks like a good plot. At this point, I have an example for you to practice in Canvas. It uses a data set which is built into R. You will see a lot of these commands as you practice multiple linear regression. Thank you so much.